the last class we had talked about the definition of fractals, the concept of fractal dimension, and we had understood that everything in nature, all the objects in nature that we see, they are all fractals, and that is to be understood in terms of the fractal dimension. Now, today we will handle the problem of generating fractals. Can we generate fractals by some kind of iterative procedure? In order to tackle that question, let us first consider a fractal with the embedding space of a line. That means, we have already learned that fractals are objects that live in spaces, embedding space, underlying space, and the dimension of the embedding space is either equal to or greater than the dimension of the fractal object. So, in this case, we are considering the simplest possible situation where the underlying embedding space is one dimensional, which means we are considering the line as my embedding space. So, it is like this. So, this is my space on which we are considering the generation of a fractal. Now, if this is the embedding space, then on that we will choose a particular chunk, particular portion on which we will try to generate the fractal, which is the distance between 0 and 1, say these 2 points. So, we are attempting to generate an object between the range 0 to 1 on the real line, and let me describe an iterative procedure in which we will first say that this distance between 0 to 1, let me first mark it that this is the range we are considering. All right. Now, in the first step, what we will do is we will divide this into 3 equal parts and then eliminate the middle 1/3, remove the middle 1/3, so that we will get, after the first iterate, something like this. Here is one chunk and here is another chunk. So, from this point to this point and from this point to this point, which means we have removed the middle 1/3. So, this is a procedure of, as it is said that it is a procedure of removal of the middle 1/3. So, this is coming from this line, full line 0 to 1 to this is one step, one iteration. In the next iteration, what we will do is we will continue this procedure, which means that we are left with, at this stage, 2 chunks. We will take each of them and remove the middle 1/3. So, we will have an object like so. From here to here, from here to here, from here to here, and thus. So, this is the second iteration of this iterative procedure, and finally, not finally, and in the next step we will have to further subdivide these 4 segments into even smaller ones and remove the middle 1/3. So, we have this and so on and so forth. If we now consider continuing this procedure ad infinitum, then what do you think we will have at the end? At the end, if you go on doing this procedure, you can see that in every step we are removing some part of it. So, we started from the real line, full real line, but in every step we are removing some part of it. Ultimately, when we do this procedure infinite number of times, what are we left with? We are essentially left with a collection of dots on the real line. Each of these segments will shrink to 0 size or will be subdivided and subdivided and so on and so forth. finally we will be left with a sprinkle of dots on the real line. They are located in some place. Now the question is, finally what we have is a sprinkle of dots, a collection of points, a set. This set is called the Cantor set. The set is obtained by the removal of middle one-third procedure. Finally, we will end up with a collection of dots. The question now is that a fractal? In order to address this question, we will have to obtain the dimension of this object. Now, in order to obtain the dimension of this object, as we have learned already, we have to divide the underlying space into boxes and count the number of boxes that are necessary to cover this object. So, here we need only to create boxes within the range between 0 and 1, and we could say that we will subdivide this into 10 number of boxes. So, 0 to 0.1, 0.1 to 0.2 and so on and so forth, and then count and further subdivide the boxes and go on counting. But it is not difficult to see that if we subdivide this 0 to 1 range into boxes in a different way, into boxes of size 1/3, 0 to 1/3, 1/3 to 2/3 and 2/3 to 1, then we have some advantage. What advantage? Let us see. After the first step, if we have divided the boxes into these 3 boxes, this range between 0 to 1 into these 3 boxes, the first one between 0 to 1/3, second one between 1/3 to 2/3 and third one between 2/3 to 1, then how many boxes do we really need in order to cover this object? 2. So, we have n is equal to 2. And what is our epsilon? Epsilon is 1/3 of the whole range. The range is 1 and therefore 1/3 of that. So, epsilon is 1/3. So, by the definition of dimension that we have already learnt about, if we look at the dimension, then dimension is limit epsilon tending to 0, it is ln n of epsilon, a function of epsilon, and by ln 1 by epsilon. That is what we have learnt as the definition of dimension. So, if we do that, if we consider the dimension that can be measured after the first iteration, first step, then we will say after the first step, if we measure the dimension, then d is equal to, then this point does not arise, we are only trying to measure this quantity. This will be ln n is 2, so 2 by ln 1 by epsilon is 3. This is a fractional number lying between 0 and 1, okay, a fraction. Now, let us, you might say that this is not the final step, you obviously go on doing the procedure over and over again. So, let us go to the second step. At this second step, if I now consider after the second step, we are here. So, this is the first step, this is the second step, this is the third step, and so on and so forth. So, we are here now. At this stage, if we say that we will further subdivide the boxes into 9 boxes, that means earlier it was from here to here, from here to here and from here to here. Now, we will further subdivide the boxes into 3 each, that means this part is divided into 3 boxes, this part divided into 3 boxes, so on and so forth, 9 boxes total. Then, how many of these boxes are now required to cover this object? At this stage, n is equal to 4 and epsilon is 1/9. So, d is ln 4 by ln 9, which we can easily say this is equal to ln 2 by ln 3. Wait. So, what have we achieved? See, by going from step 1 to step 2, we find that the dimension as measured like so remains the same. As a result, it is not difficult to conclude that if you go on doing this procedure ad infinitum, and in each step you also make the epsilon, the box length, further smaller by the same degree, that means each one is 1/3 of the previous one, then we end up after the infinite number of iterations with the same dimension. Therefore, when we have arrived at the final thing, the collection sprinkle of dots, the Cantor set, its dimension should also be the same, which is ln 2 by ln 3. This is a fractional number. So, we conclude that what we have here is a fractal. A fractal which is in the embedding space of one dimension, and therefore, that should have a fractional dimension between 0 and 1, which is true in this case. This Cantor set is very important in the study of nonlinear dynamics, and we will have to understand that in order to study nonlinear dynamics later maybe. Now, let us consider another situation where the embedding space is 2D. Let us consider another where the embedding space is 2-dimensional. Now, consider we have a square to start with. So, we have a square to start with. So, even though our embedding space is 2-dimensional, spread ad infinitum in all directions, up, down, left, right, but it will be sufficient for us to consider the range of space that is confined within this square. Now, here also we will apply the middle 1/3 removal procedure. What is it? We will remove the middle 1/3 of this square. What is the middle 1/3 of the square? It is essentially this square. Okay, if we remove that, you see what we have done? We have divided the side into 3 equal parts, and this side into 3 equal parts. So, out of that we have taken the middle one and we have removed that. So, that is the middle 1/3 removal procedure as applied in 2D space. So, this is the first iterate though. In the second iterate, what we will do? We are now left with 1, 2, 3, 4, 5, 6, 7, 8 of these smaller squares, and we will remove further the middle 1/3. So, what we will do? We will remove this. Let me do it by hand because these are smaller. Here we will remove this, or this one will remove this. And so on and so forth. So, this is the second step. In the third step, whatever squares are remaining around it, we can easily see that if we complete these, then we are left with those squares. So, here are those squares. Further, if we take these, then here is one square, another another here, another here. So, in this square there are how many left? 1, 2, 3, 4, 5, 6, 7, 8, and naturally in 1, 2, 3, 4, 5, 6, 7, 8 there would be total 64 squares left, and in the next iterate you will further subdivide these into those smaller chunks and remove them, and so on and so forth. Ultimately you will land up in, and this procedure will be repeated for each of these squares. Ultimately what will be left with? You will be left with in this embedding space of 2D, we will be left with only some parts filled, rest of the parts removed empty, and that will be a collection of points in the 2D space, another set. Another set. This set is called Sierpinski square. Now, let us consider obtaining its dimension, this particular object's dimension. Now, again we will have to cover this object, this particular embedding space with grid, with squares, because this object is a square object to start with. So, we will subdivide, but the question is how it will be most convenient to subdivide this particular box. The initial starting point is the square box. How it will be most convenient to subdivide the square box into the grids, the boxes. There, by the same logic, it will be convenient to subdivide if this is between 0 and 1, then it will be convenient to subdivide into 1/3 and 2/3 sides. So that in the first step we will make these as the boxes, and then we will ask how many of these boxes are necessary to cover the resulting object after the first iterate. So, ultimately you have obtained a particular geometrical object, the Sierpinski square, and we are asking how many of this 1/3 to 2/3 to 1 these square boxes are necessary to cover this object. Obviously, when epsilon is between epsilon is 1/3, 1/3 is the side of the box, then at that stage what is n? 1, 2, 3, 4, 5, 6, 7, 8. So, n is 8. So, at that stage, that means when epsilon is 1/3, what is the value of the dimension? Dimension is ln n epsilon, which is 8, by ln 1 by epsilon, which is 3, right. So, we have a number that is between 1 and 2. So, we have this particular number as the representation of the dimension, but when epsilon is 1/3, you might argue what happens if epsilon is brought down further. For example, it will be convenient to bring down epsilon to 1/9 maybe at the next stage. So, we have these chunks, and so we are considering these boxes as the grids, and we are asking how many of these grids are now necessary in order to cover this object. At this stage, so when epsilon is 1/9, then how many of these are necessary to cover this object? Notice there are, in this particular box, there are 1, 2, 3, 4, 5, 6, 7, 8. Likewise, there are 8 of these filled boxes, and therefore, we will need 64 of these in order to cover this object. So, at this stage, D is ln 64 by ln 9, which is nothing but ln 8 by ln 3. So, you see, even if we have reduced the epsilon further, we have obtained the same value of the dimension. So, it stands to reason that if we keep on reducing the epsilon ad infinitum, at every stage we will keep having the same value of the dimension, and therefore, the dimension is really invariant while epsilon tends to 0. So, this is the measure of the dimension of this object, ln 8 by ln 3. Fine. So, we have understood the Sierpinski square. There is another variant of the Sierpinski constructions, which is a Sierpinski triangle, which is more popular than the Sierpinski square. So, in this case, we construct a triangle as the starting point, and from there we apply the same middle 1/3 removal scheme. So, here is the starting piece, and then we apply the middle removal scheme. So, now here we have how many of the boxes? 1, 2, 3, 4, 5, 6, 7, 8, 9. So, half of that is 1, 2, 3, 4 and half. 1, 2, 3, 4 and half. So, if we now construct it this way, then the triangle is divided into 4 equal pieces, and imagine that we are removing the middle portion of that. So, essentially we are cutting this part out to be left with a triangle shape. So, here we have 3 triangles left, 1 triangle taken out. So, that is the first iteration in this iterative procedure. In the second iteration, what we will do? We will remove the next, we will take each of these chunks and we will remove further, and we will do like so. So, here this is removed, here this is removed, and here this fellow is removed. So, this is the second iterate of that procedure, where we are removing this part, this part and this part. In the third step, we will remove even further. I will drop a hand, we will remove this part, this part, this part, and so on and so forth. So, in every iterate, we are keeping on removing parts and thereby taking out some chunk from the initial set, the triangle, and so we have removed this, 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 and so on and so forth. After the whole thing is completed, this is not complete, of course, there are triangles remaining. In the further iterates, we will take again one third out of it. So, ultimately what remains is again a collection of a set, a collection of dots, and we are now considering what will be its dimension. When we do that, again we have to subdivide the embedding space into the grid. The grid has a property that something that completely covers the embedding space it equally divides the embedding space. Now, how we construct the grid is to our very much in our hands. We could say that we would do it the same way as we did for the square. That means, we take the whole box and then subdivide into squares and then count the number of squares, but it is not difficult to see that a further refined procedure would be, while we say that our grid squares or the embedding boxes, these are nothing but the triangles. That means, this is the whole triangle which is necessary to cover the whole object, but then in the next step we subdivide into these triangles that completely covers the space. In the next step we subdivide into the smaller triangles, and then we count the number of triangles that are necessary to cover this object and carry on. So, initially this step was we will subdivide this into 1, 2, 3, 4, these many triangles, so that epsilon is, what is epsilon? The side length of each triangle. That means, if the whole thing is 0 to 1, then my side length here is half. So, is half. Okay. And now at this stage, how many of these are necessary to cover this object? N is 1, 2 and 3. So, 3, right. So, at this stage, when we have subdivided the embedding space into these bigger triangles, these triangles, then your D is ln 3 by ln 2. This is a fractional number. Good. You might say that the definition has a limit epsilon tends to 0 as the definition. So, we will have to further subdivide epsilon. So, let us further subdivide into further halves. So, in this next step epsilon is 1/4, which means 0 to 1, here is 1/4, this is half, this is 3/4 and this is 1. So, these are the triangles we are considering now. How many of these triangles are necessary in order to cover this object at this stage? Notice that this has been removed, this has been removed, this has been removed. So, we need 1, 2, 3, 4, 5, 6, 7, 8, 9. So, n is 9. So, at this stage dimension is ln 9 by ln 4 is nothing but ln 3 by ln 2. So, you see, even though we are subdividing the embedding space, making epsilon smaller, we are getting the same value of the dimension, which means again by the same logic, if we go on doing this iterative procedure ad infinitum, we still end up with the same value, which is this ln 3 by ln 2. Notice that this is a number again between 1 and 2. So, the two dimensional space, in the underlying two dimensional space we have created an object which is a fractal. Well, these are procedures to create fractals, very simple procedures, and the determination of their dimension is also simple if we cleverly choose the embedding boxes. But this may not be true with all fractals, as we have learned. We will really need to take, if we take a fractal coming from nature, then we will really have to do it the grid counting way, that means box counting. We subdivide the space by placing a graph paper on that and then counting the number of boxes necessary to cover that object. But in such special cases where we are creating an object, not taking it for nature, but doing some artificial procedure to create a fractal, then their dimension can often be obtained in such simple way. You might ask that we have also talked about special types of curves, like the shoreline, the coastline of England, we have talked about that. So, can we artificially create an object that has the same kind of property, that it has an infinite length, but yet it contains a finite area? Well, there is such a curve. For example, if you start with a say we start with a triangle, we start with this triangle, say. Now, in the next iteration, next step, we do not subtract something from it, rather add something to it. So, what we do is we divide each side into three parts and add a triangle to it. So, we have this one here, some add the triangles to it. So, ultimately after this stage you have got this star like shaped object remaining. Fine. Now, in the next step, whatever sides are remaining, you again subdivide that into 3 parts and add a triangle to it. So, you will have this one divided, so add a triangle to it, this one divided, add a triangle to it, this one divided, add a triangle to it, and so on and so forth. In the next step, take all the sides that are remaining and do the same procedure. So, you will add here, you will add here, you will add here, you will add here, and continue this process ad infinitum. Now, in each step you are adding some length to it. Naturally, if you continue this process ad infinitum, after infinite number of steps, you will have an area that is finite, yet the perimeter length would become infinite. So, we can by some procedure create such objects that resemble in the essential way the character, the geometrical character of coastlines. Now, we consider another way of creating fractals. This way comes from the study of dynamics. In the study of dynamics, you have some kind of a dynamical system represented often by means of x n plus 1 is equal to some function of x n, which means that you start from the x n a particular position, you go to x n plus 1, then that process can be continued. So, that this defines a dynamical system where a point moves from a point place to place. Now, you can also say that these are vectors, that means x n and y n, to x n plus 1 y n plus 1. So, you have a x n plus 1 y n plus 1 is given as a function of x n y n. So, that what happens is, if you take a point in that space x y space, this point is a point, by this function it maps to another point and so on and so forth. So, that is a dynamical system. Now, this way we are actually doing operations on vectors, but it can be further simplified sometimes if we define this nothing but as a single complex number, which means it will have a real part and an imaginary part. So, that we will define it something like z n plus 1 is a function of z n. Where this Zn is nothing but Z real and Z imaginary. So there are two components of the Z, and you define a function which takes that particular point in the complex plane to another point in the complex plane. In doing so, let us define a particular very simple function like Zn plus 1 is equal to Zn square plus C. You have seen that every dynamical system has the variables which are Z, but they also have parameters. This is the C. So C is also a complex number, consists of complex the real part and the imaginary part. So Z is a complex number, C is a complex number, and this is a complex function that defines the next iteration of that variable Zn plus 1. So you might say that now I have the complex plane here, where this is Z real and this is Z imaginary here, and the starting point Zn is here. Then if you know the value of C, then you can obtain by computing this, you can obtain the Zn plus 1. If you know Zn plus 1, if you know C, you can compute Zn plus 2. Zn plus 2 gives Zn plus 3, and so on and so forth. You have got a dynamical system. Now, the character of this dynamical system will depend on the character of the parameter, the value of C, and C has two parts, the real part and the imaginary part. So we can also construct a parameter space where C real and C imaginary. So the value of C that we take is nothing but a point in this. What happens is that for some values of C, the iterations go to infinity. For some other values of C, this, if you go on iterating this, they remain bounded. So some values of C take the iterations to infinity, some values of C keep it bounded. So if you now say that I will construct the set, that means a set of points in C, this parameter space C, so such that if we take the C within this set, then the system will remain bounded. If we do that, then we have what is now shown in the computer screen. Just take a look at the computer screen. Here is an object in the computer screen. The blue object is that set of C which keeps the orbit bounded. And if you, for each of these values of C, you might say that there should be some region in the state space which is consisting of the real part of Z and the imaginary part of Z, some part, some set, so that if the initial condition is here, it will remain bounded. If the initial condition is out, it will go out. So for every parameter C, there will be a set in the state space for which, if the initial condition is within that set, it will remain bounded. So here is a set in the parameter space, and here is a set in the state space. What we are seeing on the computer screen now is the set in the state space, this blue set. Now the question is this a fractal? Well, for each point of this, there would be, here is in the right hand corner, you can see a particular set. If we now blow it up, you see there is a set here. This is the set in the state space, and the one earlier was the set in the parameter space. This set is called the Mandelbrot set, and this set is called the Julia set. So, essentially the Julia set is the basin of attraction, and the basin of attraction can be constructed for every value of the parameter. So, every point in the Mandelbrot set corresponds to a particular point in the Julia set, which you can see here. So, for every point in this, if I change the point, you see the Julia set is changing, which means that, see, the Julia set is changing, which means that if we now look at the Julia set, for that particular point this is the Julia set, which means that this is the basin of attraction. If the initial conditions are within this basin of attraction, then it is attracted to some kind of a fixed region. If it is out, it goes to infinity. Aren't these beautiful? You can make them even more beautiful by saying that outside this region, the region that is shown in blue, outside this region points go to infinity, but they go to infinity at different rates. So, if you now say that I will color the outside region depending on how fast they go to infinity, then we can do that by choosing proper option. Well, so here it looks beautiful, more appealing, because the outside part we have colored depending on how fast they go to infinity. And here also, if we choose a particular region, if we now move the cursor somewhere, then you can see a particular. So, this is the corresponding Julia set. Okay, if we now suppose we probe this question, is this a fractal? Here we are considering this perimeter, the perimeter of this middle blue region, is that a fractal? What we will have to do? We will have to enlarge it. So, let us try to enlarge it by moving it to a proper place and then expand it. Well, here. So, let me expand it. See, you see more and more colors and more shapes and sizes. You might say, okay, let us further enlarge it. So, we will make a particular region and then we will enlarge only that part. Fine. See, more and more colorful, beautiful shapes. Let us further enlarge it. So, you see structures within structures. You see structures within structures that were not visible unless you go probe deeper into it. And I can tell you that here is a shape, here is a structure. If you go even more deeper, you still see structures within structures, which means that this object is a fractal object. So, let me go back to the original one. Here was the original one. We said that if we choose a particular part, we see its corresponding Julia set. So, we have the corresponding Julia set. So, now let us consider what we are really looking at. We are looking at this, if you now concentrate on the image on the paper, we are considering the Mandelbrot set. This is nothing but the parameter space of the system. You know that any system has some parameters. So, for any system, electrical system will have inductance, capacitance, input voltage and stuff like that as the parameters. A mechanical system will have the forcing function, the value of the forcing function, the mass, value of the mass, the stiffness of the spring and stuff like that as the parameters. And this tells us that if we now paint a picture of the parameter space for which a certain kind of behavior will occur. In this particular case, we are considering bounded behavior. Bounded behavior will occur, then we get an object on the computer screen which is a fractal object. Again, for each point in the Mandelbrot set, if we consider the basin of attraction, that means the set of initial conditions for which the orbit remains bounded, then we get another set which is the Julia set. So, for every point of this Mandelbrot set, we are getting a Julia set. Now, here it is not difficult to write a program to do this. It is rather simple. All you need to do is to consider the complex number and consider some kind of a range. If it goes outside that range, you will paint it in one color. If it remains within that range after some number of iterations, say 100, then you paint it with another color. And this coloring scheme is after how many iterations does it go outside that range. So, here is a ready-made program that is called Fractint. I will quickly demonstrate it. This is a program called Fractint. So, first we have to select the video mode. We are selecting the video mode of this one. So, the moment you choose, you have got it. So, for every point in this, you get a range. So, now I am moving the cursor to a part that is closer to the edge. Now, if I plot the Julia set, I get a beautiful structure. Now, again I go back to the Mandelbrot set. I go to another point in the space, say here. If I now plot if I want to plot the Julia set, it is another color. So, the point that I am now making is that in this Mandelbrot set, there are infinite number of points, and for each point there is a Julia set which is a different shape, different structure. So, this is an infinitely complicated geometrical object and infinitely beautiful also. The moment you start plotting it with these colors, you find that it has immense beauty. So, now let me again do that by taking the point somewhere there. If you take a point inside, you get a region filled with the blue. That means here, if you move the cursor around it, you will find that this is the region. If you choose the initial condition beyond that, it goes to infinity, and the coloring outside the region is by the same method that I have just elucidated. That is, if it is within the red region, then it takes a certain number of iterations to go outside the area that we have said that if it goes outside that area, we will say that it is going out, running to infinity. So, how fast it is running to infinity, going to infinity, that is designated by these colors. But if you take the parameter inside the big circle, big area, big region, then you get a relatively structureless object. But if we go to the edge, then you get very many structures. So, let us illustrate it even further by showing a few points on this. If we go to the relatively smaller region, then you have got another shape of the corresponding Julia set. If you go further, to this region, you get another shape of the Julia set. Quite beautiful, isn't it? Now, if you go further up, we get a wonderful Julia set. So, the Julia sets are things of very large complexity. Now, if you want to probe the issue whether the Julia sets are fractals or not, then we can enlarge that. We have got nice pictures. Again we can enlarge some part of it, and so we see where we initially believed that these are relatively simple regions, they are not simple enough. So here if we look at each small part of it, you will still see nice fractal structures. I am now reducing this, bringing it down to an area which may be of your interest. So you see there are further colorful structures in it. So the Julia set and the Mandelbrot set have become the epitomes of fractals. But one thing that is often missed in textbooks is that they really represent dynamical systems. They really represent dynamical systems. And the lesson to be learnt is that for every dynamical systems there are parameters, and you can construct a parameter space. There are state, and you can construct a state space. This is a model, a toy model of a system that is a dynamical system, and you can have that is a dynamical system, and both in the parameter space as well as in the state space you can have fractal objects. There are certain conditions under which the basin of attraction becomes a fractal. There are certain conditions under which the set in the parameter space becomes a fractal, but in general you can expect fractals to exist in the parameter space of dynamical systems as well as in the state space of dynamical systems. This is the lesson that we have learned. It is possible to obtain the fractal dimension of the Mandelbrot set and the Julia set, but the procedure is not as straightforward as we have seen for the Sierpinski triangle or the Sierpinski square or the Cantor set. So we will leave that. You can easily obtain it and apply the box counting procedure in order to obtain it. Okay, so this will be end for today, but in the next day we will handle further procedures of generating beautiful fractal objects as a valid subject of study in geometry. Thank you very much.